Okay, so hi everybody, my name is Siyam Dangwal. I have a special guest for you. Meet John Wilson. First of all, thanks a lot for joining and accepting my invitation for this wonderful podcast. I would like to make this podcast as raw as possible so that each and every Indian audience could relate with John. So first of all, John, please kindly introduce yourself to the Indian audience.
Hi, I'm John Wilson. I'm a physicist. I'm very interested in special relativity and quantum mechanics, and I'm excited to be part of this podcast.
Okay, John. So could you please tell us about your educational qualification? From where did you have done your educational qualifications like MS and BS?
Sure. Okay, I went to Georgia Tech in the United States. I was in the PhD program in physics, in theoretical physics. I went to Georgia Tech actually as an undergraduate and in grad school, the PhD program. So I was there for about 8 years. After that, I actually became a programmer, but I kept physics as a hobby for all of these years since that time.
Okay, it's quite interesting. Okay, so the questions, I prepared a series of questions which I would like to ask to you. First of all, how do you define physics? Could you please elaborate what physics is all about?
Okay, to me, physics is the study of the natural world, the processes that happen that can be defined by mathematical equations. It encompasses all physical phenomena that happen that can be observed.
Okay, so there are various real-life examples in physics. Okay, so could you please tell the 2 or 3 real-life examples where the physics is super fun?
For me, I like special relativity. Einstein was my hero, still is my hero. I love the beauty of the mathematics that describe the world. One of my specialties is in tensor mathematics. And with tensors, you can describe the physical processes that happen in the world in a very clear and concise manner. It makes the application of physics very enjoyable.
Is physics all about remembering the bulky equations?
Okay, obviously, to be able to do physics, you want to be able to memorize equations, but it's more important to understand what the equations mean, how they apply to the real world. So it's better to build up an intuition of what the equations mean and how to process them, rather than just to memorize equations for a test. Once you understand what the equations mean, you can actually start from basic principles and build up the equations so in principle, you don't even have to memorize them. You can start from basics and determine the equations once you understand how physics works and what the equations mean.
Question is, what do you think are the scopes of physics in the future? Scope of physics in future? Okay.
Well, physics is attempting to understand the universe, and any process or any natural phenomena that happen that you can describe with a mathematical equation is in principle something that you can apply physics to. Anything that can be described by math is something physics can talk about. So I mean, it could be anything, even economics eventually could be described by physics, as an example.
Okay, so could you please take this scope of physics as a part in the research level? And please tell your experience in physics as when you were doing a research.
Okay, my experience in physics actually has been mostly theoretical, not so much in the experimental regime. My website is scirealm.org, and you can find my papers there. Mostly I've been concerned with special relativity and how it relates to the world. With special relativity, it's all about what it means to measure something. And when I say that, special relativity tells you that there are certain symmetries in the world that can tell you about how the universe works. For instance, let's say that you're measuring something. Let's say just something as simple as you're measuring the length of a pen or a pencil. Okay, what are some fundamental things that physics can tell us about this? Okay, well, let's say you've got a pen and I measure it. It's here in front of me, right? Okay, so I measure its length. But what are things that you can do and still get the same measurement? So for instance, I can take this pen and I can rotate it and I measure it. I'm going to get the same length. So that tells us something about the rotation properties of space. Let's say I take this pen and then I move it to the right or to the left, and then I measure it. Okay, that also tells us something about the properties of space. The rotation of the pen and getting the same measurement means that space is isotropic. It means it's the same in all directions. By moving the pen and measuring, getting the same result, it means that space is homogeneous. It doesn't matter where I measure it from. I could also take the pen and then wait 5 minutes and then measure it. That tells us something about time, that time has a symmetry to it. And then finally, special relativity, the most important one is one called the Lorentz Transformation, which is that I can have this pen and it is moving, and then I can measure it while it is in uniform motion and still get the same measurement. So that tells us about space-time properties. So special relativity tells us about all of these physical properties with something as just as simple as measuring the length of a pen.
Okay, so in the Indian syllabus of Special Theory of Relativity, we have some topics such as Lorentz Transformation, Galilean Invariance, like time dilation, and we have length contraction. So could you please give a glimpse of these topics in a very brief way, so that every audience get the point of what the Special Theory of Relativity in practical life is all about?
Okay, well, actually, the things that I just mentioned are a big part of it. In Galilean transformations, everyone has the same time. Time is an absolute. It's separate from space. And for many years in Newtonian physics, that's how they thought the universe operated. Time was separate from space. What special relativity did is find out that time and space are more connected than the Galilean transformation. It turns out that motion I was talking about, the measurement when something is moving, has to use something called the Lorentz transformation instead of the Galilean transformation. And the Lorentz transformation actually says that time can be converted to space and vice versa. And we have found that that is actually the truth of the matter. The Galilean transformation is only correct when the velocities are very small compared to the speed of light.
Yes, I agree with that.
Yes. Once things get moving very fast, close to the speed of light, then the Lorentz transformation becomes the operation that has to be used. The Galilean transformation is no longer applicable. Other things that come out of special relativity, of course, the most famous is E equals mc squared, Einstein's most famous equation. And when you use objects called four vectors, that equation becomes very obvious. Now, is your audience at the level they know about vectors and scalars? Yes. Okay, so in a normal three-dimensional world, you have vectors which tell you a direction like X, Y, Z. The vector tells you where you are, a position
The
in space.
direction of the
Right.
exactly.
Okay. Special relativity takes that concept and creates something called a 4 vector. And the 4 vector includes the time component into the vector. So that you now have a single entity, a 4 vector that has time and space linked together. And with 4 vectors, it becomes very easy to describe the physics of relativity. So I would highly recommend the study of 4 vectors, which are themselves a type of tensor, but they make tensors easy. With 4 vectors, you can describe positions. You also have a 4 velocity, 4 acceleration. The 4 velocity is actually very interesting. Okay, so with a 4 vector, you have position in time and space. You also have a 4 velocity in time and in space. Now, the spatial part of the 4 velocity is what you would expect. It's your motion through space. But the 4 velocity in time, you actually have a velocity in time, and it is the rate at which you age. So it's very interesting how that works. Now, here's sort of an analogy that you talked about, the length contraction and time dilation. So you have a 4 vector. You can imagine, let's say that time is in the up direction for the moment, okay? So when you're not moving in space, you're moving in time still, okay? So the 4 vector points up, we're moving in time. As we pull away from the time direction, we start speeding up in space. Like space will be this direction here, sideways. As we pull away from the time direction and start speeding up in the space direction, we are actually slowing down in the time direction. Now, this is an analogy. You actually have to use hyperbolic math to do it, but the analogy still works. As you move and start moving in the space direction, you're not moving as fast in the time direction. And hence, that gives you the time dilation effect. You're not aging as quickly in the time direction when you start moving in space. So they provide the really beautiful analogies. Another one that I really love is the 4 momentum. Okay, so again, the 4 vector has 2 parts, a spatial part and a temporal part. The spatial part of the 4 momentum is your regular momentum, the oomph that you have as you move through space. The temporal part of 4 momentum is what we think of as energy. So energy can be thought of as momentum through time. So the 4 vectors give you really beautiful concepts to describe the universe with what turns out to be relatively simple math, mostly just algebra.
Okay, so John, so could you please make a glimpse on the topic simultaneity in relativity? This is one of the result flowing from the Lorentz transformation.
Right. Okay. Simultaneity in Galilean physics was just standard. Since everyone used the same time, everything for everyone was simultaneous in time. The Lorentz transformation shows, however, that simultaneity is not what is called an invariant concept. In other words, what is simultaneous for one observer does not have to be simultaneous for another observer. And a great example that is used quite often is imagine a person that's standing next to a train, and then 2 lightning bolts hit nearby, okay? For a person that's standing still, the lightning bolts, he sees them at the same time. They're simultaneous for that person. The person that is on the train, if the train is moving though, since the train is moving, the light from the lightning bolt in front of him will reach him before the light from the lightning bolt behind him does. So it shows that what appears to be simultaneous for one person is not simultaneous for another person. And you get into the physics of what are called Minkowski diagrams and light cones. And when you draw that situation with a Minkowski diagram, it becomes very clear that simultaneity is not an invariant concept. Now, when I say invariant, things that are invariant are these measurements that I was talking about before. With the 4 vector, now the length of the pencil that we showed before, that's in 3 dimensions. But when you have 4 dimensions, you have to include time as well. So you actually have the measurement of the point at the start of the pencil and a time, and the end of the pencil and a time. Okay, when you include that, it's no longer a length, it's what's called an interval. The interval is the distance between 2 events, okay? And according to special relativity, all people have to measure the same event interval, okay? That is an invariant. And then that also brings up the concept of causality. If you have 2 events that are time separated, meaning that their displacement in time is greater than their displacement in space, they're called time separated. And all observers, doesn't matter how they are, who measures, all observers will see the same time separation or causality between time separated events. But space separated events can occur in any spatial order. And that has to do with the fact that simultaneity is no longer invariant. So 2 events that are simultaneous for one person, those are time or space separated events. One person will see them at the same time, but another person can see A happening before B, whereas another person can see B happening before A, or B happening before A. But the thing that is invariant is when they're time separated. A happens before B for all observers. So that structure remains. So causality remains. Simultaneity is relative.
This is the wonderful concept in physics. And
yes, that's why I love special relativity. It explains many things in a very clear, concise way.
Okay, so do you think there is any experimental evidence of time dilation or length contraction?
Yes, absolutely. A very good one is the study of muons coming from the upper atmosphere. Okay, so what happens is there are cosmic rays going through the universe, and cosmic rays strike the top edge of our atmosphere and interact with some of the particles there. And in the process, these particles called muons are created. Muons are very similar to electrons, except they have a heavier mass. But they're unstable, so they have a certain lifetime. Okay, when we make muons in the lab, they last for a certain amount of time and then decay. Okay, the muons that are coming down from the upper atmosphere, they're moving very quickly. And so they have a longer lifetime. So they're able to reach the ground. In a normal lab situation, when they're not moving fast, they should decay away very quickly before you could observe them. But since they're moving very quickly from the atmosphere down to the ground, they survive for a longer amount of time, and we're actually able to measure them. Whereas if time dilation was not real, they should have decayed before we can measure them on the ground. So that's a great example of actual experiment done for time dilation. But even better than that, there's now technological examples where they're making atomic clocks. that are very, very precise. And a famous experiment, they took 2 atomic clocks and put one in an airplane and flew it around the world, and then came back and compared the clocks. And then the one that was in the plane showed a time jump compared to the one that remained stationary. So there's 2 effects going on. You have relativistic time dilation due to speed, that's special relativity. And then you also have a time dilation due to gravitational potential. And that actually comes from general relativity. And the combination of these 2 effects has to actually be taken into account for the GPS system that we use to navigate with. You have the satellites in orbit sending out time signals to our phones or GPS trackers or so forth. And those signals have to take into account that the satellites are moving. So there's time dilation that slows them down when they're moving. The satellites are also a certain distance above the Earth, so they feel less of the gravitational potential than we do here. And so both effects have to be taken into account for the correct timing to come down to our navigation systems. If they did not take relativity into account, the navigation systems would go out, I believe it's in the order of hours. You could be miles off in just a matter of hours.
And how you define the Doppler effect in terms of special theory of relativity?
Okay, the Doppler effect is the shift in frequency that you find when there's a motion involved. The most commonly known form is a sonic Doppler effect. For instance, there's a siren, a car with a siren on going on the street. Coming toward you, it sounds higher, and when it goes away from you, it sounds like so. That sound is very common. The same effect occurs with light. The frequency shifts, but for light, the frequency shift is in the color. So when things are coming towards you, they get what is called blue shifted. Their color transforms toward the blue side of the spectrum. And when things are going away from you, they get red shifted. So the frequency goes lower. It's so blue shift is toward higher frequency, red shift is toward lower frequency. So that's the Doppler effect. And it's a straight out effect of relativity for light. The relativistic equations show very precisely how that works.
Okay, so how do you differentiate the longitudinal Doppler effect with the transverse Doppler effect? What is the basic difference between these 2?
Right. That's actually a great one that relativity describes. The original Doppler effect in the sonic case, there is not a transverse Doppler effect. It has to do with the directions that are involved in the transformations. The transverse Doppler effect is a Doppler effect that occurs at a 90-degree angle. So most Doppler effects are talking about it's either going away from you or towards you, okay? And in the Galilean transformations, that's all you get. But in the relativistic Lorentz transformation, there's the entire range going towards you or away from you. And then there's also the 90-degree case, which is called the transverse Doppler effect. And again, when you work out the math in relativity, there is also the one for 90 degrees. The experiments that they do for that, it's usually a rotating wheel that rotates very, very quickly. And then they measure along the radius to see that effect. And it is a real effect. It has been.
Okay, so there is one basic phenomena, red shift of stars.
Okay, please repeat.
There is one basic phenomena in the universe known as red shifting of the stars.
red shifting of stars. Yes.
Yes.
Okay.
How you can relate with this to the Doppler effect of special theory of relativity?
Okay, that one is actually not so much a special relativistic effect. That is getting into general relativity and expansion of the universe. What's happening in that case? Okay, for many years, we've known that the universe is expanding, but in recent years, in the last couple of decades, we've found out that it's expanding at an ever increasing rate. The expansion was found by Hubble, and it was one of the solutions that Einstein actually had in his general relativistic equations, and he used a cosmological constant to describe it. Now, when he originally made the constant, it was that he thought the universe shouldn't be expanding. He thought it should be static, and you could adjust the constant to make it static. But when Hubble found out that from observations that the universe is actually going away from us, the constant actually could be adjusted to account for that as well. So what happens is, okay, so space is expanding, so things are moving away from us due to expansion of space. It's not necessarily that something was moving away from you in space, but space itself is actually expanding. So you get a redshift from both effects. If something is moving away from you within space-time, like literally traveling in space-time, there's the redshift effect, but then space-time itself is also expanding. The metric is changing. And so you get a redshift effect from that as well. But that one, again, you're getting into the general relativistic, what are called metrics, how you measure things. So that's a general relativistic effect.
Okay, so this was all about the special theory of relativity. So now let's talk about your upcoming book on special theory of relativity. So what's your book is all about? Is from basic to the advanced level or intermediate level? Please tell all the glimpse of the book which you are working on.
Okay, it's a project that I've been working on for many years. It more or less is the notes that I wish that I had when I was a graduate student in physics. So it's all about special relativity, four vectors, tensor mechanics. When I was in grad school, I thought tensors were very mysterious, very advanced high-level math. But it turns out that when you study tensors in the four-vector formalism, they are not that difficult. It's mostly just algebra. It's not difficult concepts. So what I've done with the book is I've come up with this method of sort of almost like flowchart diagrams that connect various concepts. And so you can imagine a four vector is just a little structure, and then you can draw a diagram that shows how these four vectors are related. So for instance, let's say you've got the four position here. It's related to the four velocity by a derivative with respect to time. Only in this case, it's with respect to proper time. The four acceleration is related to the four velocity, again, by the derivative with respect to proper time. So you can start drawing these things out in diagrams and sort of see how they relate to each other. And so then you can get into fundamental constants like rest mass, speed of light, Planck's constant, and so forth. And you put these things in diagrams. Would it be okay if I pull up a diagram of one of them and show it on the screen? Okay, can you see this screen here?
Yeah, it's visible.
Okay, so this is what I'm talking about when I'm talking about these diagrams. So I have a four position here, okay, and it's a four vector. It has a time component and a space component, and it's connected to the various other four vectors. So here's how it connects by a derivative with respect to proper time to the four velocity. Then you have times a rest mass, or that's related to the energy, to the 4 momentum, which is an energy and a 3 momentum. It's connected by Planck's constant to what's called the 4 wave vector. And we were talking about the Doppler shifts and so forth from before. So that's connected very simply to the 4 momentum by Planck's constant. And then that 4 vector is related just by the imaginary number I to give you the 4 gradient. And one of the things that I've been very interested in the book is the relationship between special relativity and quantum mechanics. So it turns out if you start with just a position in space, okay, how can I start out from special relativity and get to quantum mechanics? And it turns out it's not that many steps. You start at position, you go to velocity to momentum, from momentum to a wave vector, and then from wave vector to the 4 gradient. Now, one of the properties of these 4 vectors is they have what's called a Lorentz scalar product, which means they have a magnitude. A vector has a direction in space-time and a magnitude. And when you start taking your magnitudes of 4 position, you get an interval in space. When you take the magnitude of velocity, you end up with the speed of light constant. When you take the magnitude of the momentum, you end up with one of Einstein's relations, equals mc squared. When you take the magnitude of your 4 vector, you start getting into properties of that Doppler shift that we were talking about. And then when you do the last one, when you take the magnitude of your 4 gradient, after you have done this process, you end up with the Klein-Gordon equation. And the Klein-Gordon equation is a relativistic quantum equation. So I've gone from special relativity to quantum mechanics in 5 steps, or well, 4 steps, really. 4 vectors and 4 steps to go from special relativity to quantum mechanics. And then the famous quantum equation I'll hear about is the Schrodinger equation. The Schrodinger equation is actually just the low speed limit of the Klein-Gordon equation. So using this diagramming process, it shows how all of these things are connected to one another. And then you can come full circle as well. When you go from the 4 gradient back to the 4 position and do the various manipulations, it tells you things like space-time dimension has 4 dimensions. You get the Lorentz transforms that come right out of the math. You get what's called the Minkowski metric, which is the flat space-time metric that you've heard about. Those are all just basic properties of the 4 position and the 4 gradient with very, very simple math. So the book is basically taking lots of these diagrams and then studying the intricacies between them. But this is my favorite diagram of all. It's what my research in physics has all been about. What's the relation between special relativity and quantum mechanics? More or less, it was the idea that, okay, for many years now, there has been this conflict. We have relativity versus quantum mechanics, and people are saying, but which one is right? Well, actually, they're both right. There's not this gap that quantum mechanics has to describe relativity. It actually works the other way. If you start with relativity, you can derive the rules of quantum mechanics. So it's a little bit reverse of what a lot of mainstream physicists have been doing.
Okay, it's a very interesting project, and I wish you all the best for this wonderful project, John.
Okay, and people can find this. It's all online. It's all freely available. You can Google my word for it is SRQM, which stands for Special Relativity Quantum Mechanics. If you Google SRQM, you'll find the book, and you can read it, or just look at random pages. And again, it's all freely available.
Could you please give me the link of this so that I will make available in the description box? So I enjoyed the podcast very much with you, John, and I have learned a very, very interesting things from you about the special theory of relativity. And for your wonderful project, I truly and from the bottom of my heart, I wish you very good luck for your wonderful project. And what you would like to share to the Indian audience?
Oh, well, thank you very much for inviting me to the podcast. I think knowledge should be available to all people, all ethnicities, all types. Everybody that enjoys science should definitely get involved in science. And there's no need to be shy. Just if you love physics and you love how it's science itself, if you want to understand how the universe works, jump in. I mean, it is amazing thing to learn, and it gives you an understanding that is just beautiful for understanding how the universe works. So absolutely, there's just, if you love physics, jump in and have conversations. I love comments. I love talking about physics, which is definitely why I very much enjoyed being part of this podcast.
Okay, thank you so much, John, for being a part of this podcast. So it's a time to sign off to the audience. So thanks a lot for watching the video.
Very much. Thank you very much.